chapter we talk about the point estimation. As we said before, actually we observe the random sample x1 to xn to estimate the unknown parameter theta or 2 theta. However, in the last section we defined the statistics which use it to make statistical inference. In this section we talk about maximum likelihood technique or methods to estimate theta or function of theta, for example 2 theta. The reason that we use this technique is the maximum likelihood estimator have some optimal property, especially for the large samples. So we first define the maximum likelihood methods. Let x equal x1 to xn be a sample from the population with PDF fx theta, where theta may be a vector of unknown parameter. The likelihood function is defined by L theta equal a theta conditional. X is actually f1 join this density function x1 to xn. So if x1 to xn is a random sample, then they are independent of each other. Therefore the likelihood function is equal to product of fxi. Definition 3.2 gives the maximum likelihood estimator. Let's for the sample point x, L hat x is a parameter value at which L theta x attain x maximum as a function of theta when x is fixed. So L theta hat x is greater than L theta x for each theta. Then theta hat x is called the maximum estimator, MLE of the parameter theta based on the sample x. So theta hat x, the maximum likelihood estimator, is given at a mode of the function L theta x. Sometimes we use log of the likelihood function, because the function log x, ln x, is the one-to-one function of x. So we use maximum L theta instead ln L capital L theta. If L theta is differentiable with respect to theta, the MLE of the unknown parameter theta is obtained by solving this equation. Okay, so in fact, finding the MLE of theta is a simple way to find the maximum L theta conditional on x. Then if L theta is differentiable, we can use maximum by the derivative or solving this equation and look at the second derivative of L theta respect to theta square. For example, let x equal x1 to xn be a random sample from binary binary density b1 and theta, then fx has this form, fxi. So the likelihood function is given by is product of fxi is product of this 4, and we have this equation. So the log likelihood function is given by getting log from this likelihood function and have that. If we look at the derivative of log likelihood function, we have this 4, make that 0 to solve this equation, give theta hat equal the x bar. If you look at the second derivative, we have this one which is negative, so theta hat make the that is the maximum of the L theta or log likelihood or likelihood function. Now look at the second example 3.2. Let x1 to xn be a random sample from density function. This one, it is a distribution is a density function of the beta distribution with parameter 1 and theta. From the MLE of theta, the likelihood function is given by that one, and here and that. The log likelihood is given by this equation, and the derivative of log likelihood respect to theta is given by n over theta plus summation ln xi. When make is equal to 0, we'll find theta hat at that form, and second derivative is also negative, so theta hat is a maximum value. Let second example, let x1 to xn be a random sample from density function here, and we look for the MLE of theta. The log likelihood function is that, and likelihood function is that, and log likelihood given by this equation, and we can obtain the MLE of theta by solving this equation to have this solution. Example 4. We want to obtain the MLE of theta when x1 to xn is a random sample of uniform distribution 2 plus theta and 3 minus theta. So the density function is given by that form, where 2 plus theta less than first order statistic and less than n order statistic and less than 3 minus theta. If solve it this non-equality, we get two non-equality, theta less than x1 minus 2, theta less than 3 minus xn. So the likelihood function is that one, this x1, and all xi are between 2 plus theta and 3 minus theta if x order n and x order 1 satisfy in this non-equality, or theta satisfying two non-equality here, so they are that one. We can write this formula to that one, because when the mx is the minimum x1 minus 2 and 3 minus xn. The likelihood L theta is decreasing. So if you look at of the likelihood is a decreasing function, and the maximum obtained when theta get theta get the mx. So the ml of theta is given by the mx, which mx is minimum x1 minus 2 and 3 minus xn. Actually, if look of the definition of the MLE of theta, when look at the likelihood function, the likelihood function is the joint density of x1 to xn. Actually, the likelihood function is the probability of observe x1 to xn, the sample x1 to xn. So when you find theta hat which make the likelihood function maximum, in fact we found the theta which the maximum the probability of the sample, which is a best way to know, because this sample is happens, so this sample has the maximum chance of the happens. So when you put when you put the hat here, we find, in fact we make that function maximum, or because the samples happens, so this sample has the maximum chance to happens, is a reality looking for the maximum likelihood methods. So in the case where theta 1 r theta 1 to theta k is the vector, is not the only one value, we can look for the solving this equation. Okay, it is simple to use this form of equation and look for the derivative of the log likelihood for respect to every theta j. For example, let x be a x1 to xn be a random sample from the normal distribution mu and sigma square, and we suppose mu and sigma are unknown parameters, so the likelihood function given by this formula and log likelihood has this form. Okay, we take derivative respect to mu and respect to sigma square, and solve these two equation to obtain mu hat equal x bar and sigma hat 2 is equal summation xi minus x bar square divided by n. There are another example. Let x1 to xn, y1 to yn be two random samples from an exponential distribution with parameter theta and alpha theta respectively. We look for the MLE of the theta and alpha when xi and yi are independent. For example, like the factory has two product line, and x1 to xn is the product of the n day of the first line, and y1 to yn is product of n of second line. Two lines are independent, which so the density of xi and yi given by that one, and the log likelihood is product of fxi theta fyi theta, because xi from yi are independent and have this function. So the log we can get log from this likelihood function to have this log. So we calculate derivative L theta and alpha with respect to theta and alpha as well, to find theta hat is second x bar plus alpha hat y bar, and here is alpha hat equal 1 over theta hat y bar. We have two equations, and we get the unique solution for that if solving this equation 3.1 and 3.2 we obtain the maximum likelihood of theta and alpha is equal theta hat equal x bar minus theta alpha hat is x bar over y bar. So as we discussed in the last section, exponential family is a large class of distribution, of density of distribution, and here give the methods to find the MLE of the parameter of the multi-parameter exponential. Let x1 to xn be a random sample of the co-parameter exponential family, which density of that one if defined to star j equals summation I equal 1 to nt jxi, and the ML of theta 1 theta is found by solving this equation. So it's a simple method to obtain the MLE of the multi-parameter exponential. The proof is very simple. So if you look of this density function, the log likelihood given by this 4, and the log likelihood is a constant plus summation j r from 1 to cot theta j t star j, and plus n d theta. If we get derivative of log likelihood respect to theta j, we have this for, so we know the expectation of log likelihood respect to theta j is equal to 0, therefore we have that one. And if using this equation equal 0, we had rho theta L rho on respect to rho theta j equal to 2j star minus expected tj, and solving equation is give that formula. For example, let x1 to semi negative exponential, t star is summation xi, and expectation t external is equal n, expecting xi is n over theta. By setting that one, we can find summation xi equal n theta, and theta at is x bar, the m. So the likelihood function in the multiple exponential family is very simple, and we can find MLE of the different type of distribution, which give some example here, and students can examine different example to find the MLE of unknown parameter. In the next section, we talk about the optimal probability of the maximum likelihood. This optimal probability make the likelihood maximum likelihood methods very popular in the statistical inference or in the applied statistics as well.